Bismillahirrahmanirrahim. Dear students, grade 11, and the lecture number is 59, and we are doing chapter number 9, chemical kinetics. We are doing chapter number 9, chemical kinetics, and the topic is order of reactions. Order of reactions. So, number 1 is the first order. First order reaction. Reaction is directly proportional to first power. First power. Like this. A1. First power of this one. So, a reaction whose rate of reaction is directly proportional to first power of the concentration of single reactant. First power of single reactant is called first order reaction. So, side by side I am going to explain these. The molecule is 2 moles of N2O5, and it is going to decompose to give 2 moles of nitrogen tetroxide and oxygen gas. The students, according to experimental studies, this reaction is first order kinetics with respect to N2O5. According to the experimental studies, in the order of reaction, you can see first power of the N2O5. I told you that order of reaction is the experimental determined quantity. By using this equation, by seeing this equation, we are not going to get a result, because this is the purely experimental determined quantity. So the examiner will give you some hints. Either he will give you this rate law, or he will give you a step. Similar step is called a rate determining step. So he must mention the rate determining step. Just by seeing the chemical equation, you will not decide the order of reaction. This is very important, because order of reaction is purely experimental determined quantity. You can see here, it must be second order because 2 molecules are here. But according to experimental studies, it is the first order. So this is the first example. Second, ammonium nitrite. Ammonium nitrite. This is a slow step, and this is a rate determining step. Ammonium nitrite. Decompose to give a nitrogen gas plus 2 water molecule. Okay. So this is a slow step. Must write like this. This is a slow step, and this is the rate determining the step, because according to the rate law, directly proportional to the first power of ammonium nitrite. Okay. It means that this chemical reaction complete in the first step, and it shows a rate law here. So this is the first order reaction whose rate of reactions directly proportional to the first power of the concentration of single reactant is called first order. Now second order. Second order. In the second order reaction, rate of chemical reaction is directly proportional to the second power. Like this one. Second power of the reacting substance, or directly proportional if you have 2 reactants. Okay. This is also second power. Two reactants, 1 plus 1, 2, or if single substance multiply by 2. This is a second order reaction. Reaction for which sum of exponents of reaction is 2. 1 plus 1, 2 is called second order kinetics. So here the example is given same. This is also slow. 2 moles of nitrogen dioxide going to be 2 moles of nitric oxide and oxygen gas. So this is also slow. Slow step is called a rate determining step. So this chemical reaction complete in the first step because its rate law is directly proportional to the second power of the reactant. This is the second power. So this is the second order reaction. So we have another also. You can see nitric oxide plus ozone changes into nitrogen dioxide and oxygen gas. So students, this is also slow step and rate determining step because according to the rate law, concentration of first power of nitric oxide, concentration of first power of ozone, so 1 plus 1 is equal to, so this is also second order reaction. So, but other case, if you have 2 moles of nitrogen dioxide and ozone gas is there and you will get N2O5 and oxygen gas. So this is not first step completion because 2 moles are here and 1 mole is here. So according to the experiment, the rate law is going to be shown here. 1 molecule of the nitrogen dioxide and 1 mole of the ozone. So 1 plus 1, 2. So this is not complete in the first step. So dear students, this is called a second order reaction. Some of the exponents of the reactant must give the 2. Then on third order. Now, third order reaction. In the third order reaction, the rate of the reaction is directly proportional to maybe this or maybe this or maybe this. Sum should be 3. 3 must be 1 molecule participating. There are 3 multiplication. If the 2 molecules, either 2 here, 1 here, or 2 here, 1 maybe here, and maybe 1, 1, 1. So this is the third order. The reaction for which the sum of the exponents of reaction is 3. Sum of exponents, when you sum them, when you add them, your result should be 3. So here is an example for you. 2 moles of nitric oxide and 1 mole of oxygen to give a 2 moles of nitrogen dioxide. This is a slow step and rate determining step. So that's why rate is directly proportional to concentration of nitric oxide power 2 and the concentration of oxygen. So this is the 2 plus 1 is equal to 3. So this is the third order. So this in the first step, this chemical reaction is going to be complete. If you look this chemical reaction, 2 moles of ferric chloride, 6 moles of potassium iodide to give 2 moles of iron iodide plus 6 moles of potassium chloride plus iodine here. So actually this is a 6.6 plus 2, 8 order. But this is going to complete in the more than one step. So that's why rate law is directly proportional. Concentration of the 1 mole of the ferric chloride in the rate determining step and 2 moles of potassium iodide. So 2 plus 1, 3. So in the experimental observations, then this chemical reaction is going to be completed in more than one step. So 2 moles of potassium iodide participate and 1 mole of ferric chloride participate in the rate determining step. That's why it is going to be called a third order. Then there is another one, fractional order. Fractional order. Means 0.5 like this. The reaction for which sum of exponents are rate is a fraction. We call fractional order like this. You have a hydrogen plus bromine to give a hydrogen bromide, but according to the rate law and the slow step, which is a rate determining step, according to experimental evidence, that 1 mole of hydrogen and half mole of the bromine means 1 atom. Half mole of bromine is going to participate in the rate determining state. So 1 plus 0.5 is equal to 1.5 order. Fractional 1.5 order. Same case for also there another example you have chloroform CH chloroform is going to react with chlorine, so you will get carbon tetrachloride and plus HCl. So this need only 1 chlorine here, but there are 2. That's why according to the rate law and also rate determining step, so 1 mole of the chloroform participate with the half mole of chlorine. So again 1 plus 0.5, so 1.5. Order is 1.5. The reaction for which sum of the exponents of rate equation is a fraction is called fractional order reaction. Then the last one is a negative order. Negative order reaction. In the negative order reaction, the sum should be negative. The reaction for which sum of the exponents of rate of reaction is negative is called negative order reaction. So here 2 moles of ozone going to change into 3 moles of oxygen. This is the only one reaction order that you can see there the participation of the product. Otherwise we have no participation of the products. Rate law is directly proportional to the concentration of ozone and the concentration of oxygen. So when the concentration of oxygen doubles, the rate becomes half. When the concentration of oxygen doubles, the rate becomes half. So this is called a negative order. Now there is a self-assessment for you. The following reaction. So these are the order of reactions we complete. Now there is a self-assessment for you to solve it. Reaction is 2 moles of hydrogen plus 2 moles of nitric oxide to give a 1 mole of nitrogen and 2 moles of water. Self-check exercise 9.2. He said that following reaction is the first order in hydrogen. So rate is directly proportional. He said first power in hydrogen. Okay, this is a hint. And second order in nitric oxide. Okay. Second order in nitric oxide. First order in hydrogen and second order is in nitric oxide. This statement is given. Because if you see this in fourth order, 2 plus 2, 4, but the rate law and also the experimental evidence suggests that only one molecule of hydrogen is participate and the two molecules of the nitric oxide participate in the rate determining step. So write the rate law for the both. So rate law for the both whole is rate directly proportional concentration of the first power of the hydrogen and 2 powers for the nitric oxide. So 1 plus 2 is equal to 3. So the order is third. Third order reaction. So this is a third order kinetics. Third order reaction kinetics. So students, these are the order of the reactions. Chapter number 9, chemical kinetics. Then the topic is collision theory. Skipped many topics, numericals, they are going to be skipped. Collision theory. Many pages are going to be skipped. If you see article 9.3, not 9.2. This is the 9.2 collision theory, transition state and activation energy according to your reduced syllabus. Collision theory, transition temperature, transition state and activation energy. So 3 topics we have to discuss here. Collision theory and transition state activation energy. 3 topics. Dear students, you done in the gases chapter. So when you have a closed container and some gases are there, suppose there is a helium gas and hydrogen gas, both gases are present in the closed containers. So the property of gas is to move. It has a kinetic energy. It is going to move in a straight line until unless it collides with the wall of container or with each other to change the direction. Collide, collisions. So dear students, if these collisions occur and no chemical reaction taking place, means when the gas molecules collide with each other or with the wall of container, there will be no chemical reaction. So these collisions are called perfectly elastic collisions, ineffective collisions. During these collisions, no reaction takes place. Ineffective collisions, elastic collisions. This is one thing. If there are 2 reactants and they are going to be combined with each other and the reaction takes place, It means that these reactants, they collide with each other, and during the collision, the some product is going to be formed. It means that their collisions are effective collisions. So these collisions are effective collisions. So only the effective collisions are going to form the chemical product. That's why collisions theory has been proposed to explain the observed kinetic interactions of the reactants. For a chemical reaction to occur, the combining atoms or molecules must collide with each other, and these collisions must be effective collisions. Then the chemical reaction takes place. These collisions may be effective, may be ineffective, I told you. Ineffective, no product. Effective, you will get product. The effective collisions can take place only if the energy of colliding particles is high enough to overcome the repulsive forces present between around the reacting particles. Means there must be the enough energy to overcome the repulsive forces between the reactant molecules to form the products. So that is why proper orientation is going to be needed for the colliding particles. It means that during the collisions, these particles require fixed, appropriate, fixed energy, proper energy to break the bonds, to form new bonds. Because in the chemical reactions, old bonds are going to be broken down and new bonds are going to be formed here. So that's why we should have activation of energy. The minimum amount of energy in addition to the average kinetic energy which the particles must possess for effective collisions. It means that if there are effective collisions, then the reaction will take place. Otherwise, the chemical reaction will not take place. So, minimum amount of energy in addition to the average kinetic energy which the particles must possess for effective collisions. The reaction will not occur if the energy of reacting place is less than that of the activation energy. If the reacting particles have less energy than the activation energy, no chemical reaction will take place. So that is why the rate of chemical reaction depends upon activation of energy. The greater the activation of energy, lesser will be the rate of the chemical reaction. There are many examples for this one. If you see, you done in the grade 10 preparation of the ozone in the atmosphere from the nature. There are different layers of atmosphere. We are living in the troposphere, and upper there is a stratosphere. This is called ozone layer, about 20 to 25 kilometers. So there is the ozone, and ozone layer which is protected from the very dangerous ultraviolet rays coming from the sun. So when these ultraviolet rays hit the ozone, so this ozone is going to be changed into oxygen and gas and nascent oxygen, atomic oxygen. So this again atomic oxygen and the oxygen molecule to form the ozone. So that's why balance. The concentration of ozone is balanced, destruction and formation at the same time. So it means that at that time the energy of activation is very high. Activation of energy is very high. That is why ozone is not going to be destroyed. But in the presence of catalyst, chlorofluorocarbon, I'm not going to detail here, chlorofluorocarbon, they reach in the stratosphere, and when the ultraviolet light hit these chlorofluorocarbon, catalyst chlorine atom is going to be formed, free radical chlorine is going to be formed, which is going to react with the ozone and the activation energy decreases down in the two steps, and the concentration of ozone is going to be less. So we call depletion of the ozone. So this is the activation of energy. If activation of energy is very high, the reaction of the chemical reaction will be slowed down. This is because only the small fraction of molecules possess enough energy to react. On the other hand, if the activation energy is small, then the larger molecule can bring about the effective collisions. I told you by using catalyst, that activation energy is going to be decreased, path of chemical reaction is going to be changed, and the reaction is going to be proceed with a high rate. So just I am going to give these examples. Dear students, this is the A molecule and B molecule. They are going to react with each other. So if there is enough activation energy, then there is a formation of product. But before the formation of product, there is an intermediate state, transition state, complex formation state. So this is the intermediate state, means the bond between A and B are going to be formed. And bond between A and A is going to be broken down. Bond between A and B is going to be formed. Bond between B and B is going to be broken down. This is the activated complex. This is the transition state, intermediate state. Transition state, intermediate state. It depends upon the life of the chemical reaction. If the chemical reaction fast, its life will be very, very short. Means suddenly it will be changing the product. If the chemical reaction is very slow, so its life will be long, so it will be changed very slowly to form the product. Now you will get A, B molecule and A, B molecule, or like this one. So you will get a product. So this state is called a transition state. So dear students, we are going to finish here. I will continue this lecture. This is a very important activation energy. There are many examples. Also you have to see endothermic reaction and exothermic reactions. Then we have to draw the graph for this one. Then see how the activation energy is going to be involved. Thank you very much.